In this video, I'll go through how to calculate winding impedances for 3-winding transformers and kind of make the what's called a T model, which is important for some studies. So what I'm showing here, I'm showing just single phase. So you can think of it as single phase or per phase basis. But just remember for three phase, you would see three phases. So if you have like let's say you have grounded Y, just for simplicity, basically the wind. So you have a Y, neutral, you'd have another Y, you have another Y. So if the high side is H1, H2, H3, this would be HO. Secondary would be X1, X2, X3, XO. Then tertiary would be Y1, Y2, Y3, for instance, and Y0. This is just an example. So this is more, so three phase. But we know transformers are balanced. Everything is kind of the same. We don't have to do the analysis in three phase. You can do it in per phase, which is a lot simpler, and it just kind of makes things that are kind of easy to kind of go through. So what I'm drawing here, basically as if I just took one phase. So if this is one winding and this is one winding, this is one winding of each transformer. So that's what I'm showing here. So here's primary, P primary, secondary, and tertiary. So this is if kind of show winding. So you have kind of, let's say, start of the winding, then you wind the turns, then you reach the finish. So kind of the finish of the winding. The same thing here, and I'm not showing polarity and other things, because that's not the intent of this video. But what you see in textbooks, for instance, or some white papers or reports, you might see something like this instead, where they just show like here's one winding, here's this means primary, here's another winding. So they don't show kind of like start of each winding. And again, I'm not showing taps or anything, just for simplicity. Then from modeling purposes, you would show here's kind of the terminal of one phase of the primary. So you have the winding here. So this is the winding, so it has turns or loops. Then this point here is a junction that joins the one side of the primary. Here's the terminal of the secondary, terminal of the tertiary. But just remember, this here doesn't mean this is a Y, because what I'm drawing here is this is per phase. I'm just showing one phase per winding, per side. Like here's one phase of the primary, one phase of the secondary. And for modeling purposes, this does not mean it's a neutral. Like this neutral here or this point here does not have any physical meaning. It's not like this neutral when you have three phase. It's not the same. This is just for modeling purposes. This is one way you can model a three-phase winding transformer. So then how do we determine? So again, if I go to that model, so if I go back to that model, so here's the primary terminal. Again, I'm just showing one phase. Then here's the terminal of the secondary. Here's the terminal of the tertiary. Another way some people will, and typically this is referred to as the T model. Some people might represent it like this, which looks like a T That's why they call the T model. And the T model you can construct regardless of whether you have a tertiary or not. Because if you have a two-winding transformer, if you have just a two-winding transformer, you can still construct the T model. So here's the primary side, here's the secondary side, and the tertiary, basically this here, since you don't have a tertiary, this would be kind of the tank. The connection, because if you think about flux will be induced. So if you energize, let's say you energize the high side or primary, I'm going to say primary, because primary, high side can be primary or secondary. It depends on step up, step down. Because if you have a step up, like a generation, for instance, you step the voltage from 20 kV to 345 kV, the primary in this side is the 20 kV, which is a low voltage. If it's a step down, it's the opposite. But anyway, and assuming this is connected to a load, for instance, so you have the core kind of, because I'm assuming core form here. So the windings are wound around the core leg or legs. And so this winding will establish flux in the core, and that flux will induce voltage in the other winding. But that flux, some of it it's not going to be contained, all of it is not going to be contained within the core. Some of it will leak out of the core, and it's going to go, because if you imagine there is the tank here, around kind of the core and coil is inside. So some of this flux here will go through the tank and come back through the clamps, and then the yokes, then make it back to the core. So if you think about, you can think of this here as one turn made up from basically going from the core to the tank, then back to the core. That's what we represent as this tertiary here. But anyway, now then, and you can do tests. So what I'm showing here, positive sequence basically, because zero sequence will be, the test will be different, positive sequence impedance. And I did some other videos on how to determine the zero sequence. But then basically, and this resistance here is not the DC winding resistance. These resistances that I'm talking about here, they are AC. So they are due to leakage and also the winding resistance. So on top of the DC winding resistance, because the winding has a conductor which has resistance, but it also, you're going to have some leakage flux that will cause extra losses in anything that's kind of surrounded the core and coil, like the core frames, the tank, and so on and so forth. So just keep in mind, the resistances that I'm talking about here are not DC. These are AC. They are AC resistances, and they can be per unit or percent. And typically, this resistance here, you take the losses that you measure in watts divided by the volt ampere rating, of that transformer. So, then if you multiply, so this will give you per unit. If you multiply by 100%, you get the percent resistance. So this is a resistance. So it's not DC basically. But anyway, since it's leakage, so you measure resistance between winding 1 and 2. So winding 1, for instance, if we call primary as winding 1, secondary 2, tertiary 3, basically you get, because if you think about, if you look at from the top, you're going to have the core here. So this is the core leg. If you look at it from the top, basically cross section, then the tertiary, for instance, might be kind of next to the core. They're going to have some gap, some insulation in between for dielectric. Then you're going to have the secondary, then you're going to have some gap made up of insulation, oil, and other things, because you have to make sure you meet the dielectric requirements. Then you would have the primary or high side. So because the core will have that flux, and some flux is going to link the tertiary, but it's not going to link the secondary or the primary winding. So that's what we call leakage, because it does not make it all the way to the other winding. So then the resistance between winding 1 and 2 is just the resistance of winding 1 plus resistance of winding 2. Again, these are not DC resistances that you measure with an ohm meter. That's not what these are. These are leakage. So you can think of them as self-resistances, basically. Each winding will have a resistance due to the conductor, as well as leakage. That flux that only links, for instance, R1 is just the resistance of winding 1 plus the extra losses caused by leakage flux that links winding 1 only. It does not link the other windings. Then R13 is R1 plus R3. R23 is basically the resistance between winding 2 and 3 is the resistance of winding 2 plus resistance of R3. Then if you take these equations here, you manipulate them, because if I want R1, I see R1 is here and is here. So now if I sum these two, then kind of manipulate them to get rid of R2, R3, because I don't need those. I only need R1. And if you solve for R1 only, you will get this equation here. That's all I did, basically. But I didn't show all the derivation. So what you will get, R1 is 1/2 times R12 plus R13 minus R23. In other words, because this is R1, what you notice here, you sum up the resistances that involve 1. And the one that does not involve 1, subscript 1, it gets subtracted. So the same thing with R2, because you see 2 is involved here, so it's summed up, it's added. This one is subtracted because you don't see 2. The same thing with R3. Then you subtract the one that does not involve 3. And you can do the same thing for reactance. So the leakage reactance between winding 1 and 2 is the self-reactance of winding 1 plus the self-reactance of winding 2. And the same thing with X13 and X23. Again, if you take these, again, so if I call this equation 1, 2, 3, so if you take 1 plus 2, it will give you 2x1 plus x2 plus x3 is equal to x1, 2 plus x1, 3. Then x1 is 1/2 times x2 plus x3 plus x1, so is equal to 1/2 times x12 plus x13 minus x2 minus x3. Now I have to get rid of x2 and x3, so then you use the other equation here, because x2, x3 is just x23. So this here ends up being 1/2 times x12 plus x13 minus x23, because from this equation here. Then if you solve for self-reactance, so x1 is just 1/2, again, kind of like resistance. You add up the ones that involve the same subscript, like in this case 1. You see one here, you see it here, so you add those up. You subtract the one that does not involve the subscript of the self-reactance. So you end up with these here. Then how do you get these values from the test? Again, if I go back to, and I'm just going to show single phase again just for simplicity. So you have the 3 windings here. So if I want, for instance, x1, x2, so so this is winding 1, winding 3, winding 2, 3. So you apply AC voltage until rated current, so rated current of the winding you energize is circulated. Then before you apply that, you short. So I'm going between 1 and 2, so I'm going to energize 1, and you can do the same thing. You can energize 2 and short winding 1. You should get similar results. Then this one here should be left open because it's not involved. So because I'm only doing 1 to 2. So you're going to circulate current. So then, because you have the core, so you have some leakage, and also you will determine R12 because you're going to measure, in this case, you're going to measure losses, load losses. You're going to measure the voltage, and obviously you circulated the rated current. Then R12 is whatever losses you measure times the voltage times amps, and this is in watts. So because you have to be mindful of watts, because you might measure losses in kilowatts, then you just convert them to watts times 100%. This will give you the resistance in percentage. Then reactance is the same thing. It's just voltage. Reactance is the voltage you applied or you measured, or just voltage divided by rated voltage of the winding you energize. But just keep in mind, if you measure this line to neutral, this has to be line to neutral, otherwise you're going to be off by a factor of √3. So you don't want to, for instance, you measure this line to neutral and put line to line here, because your result is going to be incorrect. Then kind of the same thing, if you want to measure x2 to 3, basically the principle is the same. So if we call this winding 1, 2, 3, again I'm just showing one phase per side just for simplicity. So 2, 3, so that means I'm going to short 3. This will remain open because it's not involved. I'm going to energize winding 2. So kind of the same principle, and when you do this test, you will measure, again, losses, because you're going to have a watt meter connected. You're going to measure the voltage that was dropped during the, and obviously you apply the rated current. If somehow you could not apply a rated current, then you have to, because then I take this back here. So this is not, sorry about that. You're going to measure the total impedance actually between, in this case, 2 to 3. So the total equation is voltage you measure divided by the current measured divided by rated voltage, rated current, which would be measured voltage divided by measured current times I rated. This is in general, divided by V rated. Just be mindful, be consistent. If you use line to neutral, you use this as a line to neutral, and this as a line to neutral. So obviously if you circulated a rate current, this here and this will cancel out. But if somehow you could not circulate a rated current, then you have to use this equation. So this will give you the total impedance. Then for resistance, it's still this, so 2 to the 3 is still whatever losses you measured divided by the volt times ampere times 100 if you want in percent. Then the reactance is just square root of impedance squared minus, so between 2 to 3 in this case, between resistance squared. So that's how you kind of, and this these impedances are important, you know, for running some system studies like short circuit, for instance, or Power's law. Thank you and have a great day.